f of x refers to that entire summation. F sub I of x refers to a single component, okay? So if you were to try to solve, that is to minimize this cost function, neural network, SVM, what have you, using gradient descent, that's what one iteration would look like. Because it's a finite sum, gradients are linear operators, you know, gradient of the sum is the sum of the gradients, so that's gradient descent for you. And now I'll just ask a rhetoric question that if you put yourself in the shoes of, you know, algorithm designers, some things that you may want to think about. What may you not like about this iteration given that big N, big D story that I told you? So anybody have any reservations or about drawbacks of this iteration? Any comments?
It's a pretty big sum.
It's a pretty big sum, especially if N is, say, a million or some bigger gazillion style number. That is definitely a big drawback. And that is the prime drawback for large scale, that N can be huge. There can be a variety of other drawbacks. Some of those you may have seen previously when people compare whether to do gradient or to do Newton, etc. But for purpose of today, for finite sums, the big drawback is computing gradient at a single point. There's a subscript xk missing there. Involves computing the gradient of that entire sum. That sum is huge. So getting a single gradient to do a single step of gradient descent for a large data set could take you hours or days. So that's a major drawback. But then, okay, if you identify that drawback, anybody have